I'm Vivian Shwaikani. I'll be explaining you part 2 of chapter 4, chemical equilibrium. Let's start with the objectives. In this lesson, we have to recognize the shape of the kinetic curves in a reversible reaction. We have to distinguish between homogeneous and heterogeneous equilibrium. And finally, we have to recognize the expression of the equilibrium constant Kc. Let's do a recall of the last chapter or the last part. We said last time that a chemical reaction can be either complete or incomplete. A complete chemical reaction, it means irreversible. So the reactants are transformed into product, and this is the case of, as I said, the whole chemical reactions studied so far in previous grades. While incomplete chemical reaction is called reversible, and the reactants and the products are present at the same time. Also, we defined the chemical equilibrium, that is the state of a reversible reaction where the rate of the forward reaction equals that of the reverse reaction. We said also that at equilibrium, the reactants and the products are still present, and we said that the chemical equilibrium is said to be dynamic. And you know why dynamic? Because both reactions, the forward and the backward, are moving or are occurring at equal rates, and this is the example we discussed last time to explain the word dynamic. Let's start now by the kinetic curves of reversible reaction. For this reason, consider the following reversible reaction. N2O4 gas will give me 2NO2 gas. Initially at time t0, the rate of the forward reaction is high, fast, and it decreases until it reaches a constant value at a given time t. Why it decreases? Because simply the concentration of the reactants are going to decrease with time, and concentration is a kinetic factor. Okay? So, and pay attention that it reaches a constant value at a given time t. Now the rate of the backward reaction is very low at t equals 0, and it increases slowly or gradually to reach also a constant value at a given time t that is equal to the forward reaction and at the same time t. This is equilibrium, as we said last time. At time t above, the system reaches an equilibrium state. It is said to be at equilibrium at time t, that is written t eq. Now, for the same reversible reaction considered in the previous slide, the evolution, it means the variation of the concentration of the reactant and the product with time, is shown in the below graph. Look, for N2O4 is a reactant, so at time 0, its concentration is maximum, and it decreases, as you saw in kinetic, to reach here a constant value. So at that time, this is equilibrium. There is no more change in the concentration. The concentration of this reactant, that is N2O4, becomes constant. The same for NO2. Look, at time 0, because NO2 is a product in this case, so its concentration at time 0 is 0. Its concentration starts to decrease, and then it increases to become or to have a constant value here at time, which is equilibrium. Now look, after equilibrium, what do we notice? That the concentrations of both reactant and the product become constant. For reversible reaction, equilibrium can be reached from either direction. What does that mean? To understand this idea, let's consider this equation. We have N2 plus 3H2 will give me 2NH3. Now, N2 and H2 are in this case reactants, and NH3 is the product. Look, the concentration of N2 is here, is in blue. So, it has a given value initially, and it decreases with time because it's a reactant until reaching a time t, which is t equilibrium, and it becomes constant. The same for 3H2, which is a reactant. Look at the kinetic curve of it. It starts by a maximum value, it decreases till reaches a constant value at equilibrium. Now you know why this difference in the initial concentration in N2 and H2. Because facing one N2, there is 3H2. The concentration so of H2 is 3 times more than that of N2. But now we were not discussing the issues of stoichiometric coefficient. We have just to understand what does this idea mean. So, for NH3, which is the product, at time 0 the concentration is 0. It increases to become constant also at equilibrium. Now, let's consider that this reaction has started, or we have written it in another way. Look, the product here becomes a reactant and the reactants become product. What about the curves? Look, that of NH3, which is a reactant, it's like here, the orange one. So its initial concentration is maximum. It decreases until reaching a constant value at time, which is T equilibrium. While that of both products, in this case N2 and H3, look, this is the curve of H2 and this is the curve of N2. Now, if you have to compare these two curves, you will notice that after equilibrium, this is the green, the orange, and the blue curve. Here is the green, the orange, and the blue. They are identical. So the concentration are the same after equilibrium is achieved. This is why we said that equilibrium can be reached from either direction. So it doesn't matter whether we start with N2 and H2 or whether we start with NH3. Now, what is homogeneous equilibrium? Simply, an equilibrium is homogeneous when all constituents, it means reactants and the product of the reactional system, are in the same phase. Look at these two examples. Look at this. Here we have two reactants and one product. All of them are gases, so they are found in the same phase. This is why the equilibrium is homogeneous. Look here. All reactants and products are found in an aqueous phase, so also they are in the same phase, and this is the case of a homogeneous equilibrium. What about heterogeneous equilibrium? An equilibrium is heterogeneous when the constituents of the reactional system are in different phases. Look at this example. Here I have PbI2 that is solid, while the other the products are aqueous. Aqueous and solid, it means we are in two different phases. So the equilibrium is said to be heterogeneous and not homogeneous. Consider another example. Look, this one is solid, solid, gas, and gas. Also here, the phases are different, and thus the equilibrium is said to be heterogeneous. What about the equilibrium constant? Is a very important idea called Kc. Look, at equilibrium, we said that the concentrations of reactants and the products are constant. Experimentally, scientists proved that these concentrations are related by a relation that depends on the stoichiometric coefficient of the reactants and the products. Look how. Consider this chemical reaction. This in general, it's a general representation for a chemical reaction. Look here. This is the concentration of one product, that is C, exponent, this is small c, which is the stoichiometric coefficient of C, multiplied by the concentration of the second product D, exponent, its stoichiometric coefficient, divided by the concentration of reactant A, exponent, its stoichiometric coefficient A, and multiplied here by the concentration of the second product, reactant B, exponent, its stoichiometric coefficient. As I said, this value, the value of this relation is found experimentally to be constant at equilibrium. Thus, the chemist called this constant Kc. It is called the equilibrium constant, that is denoted by Kc. So from now and then, what is Kc for you? Kc, it is simply the product of the concentration of any a product in a chemical reaction, exponent their stoichiometric coefficient, divided by the multiplication of the concentration of any reactants in a reversible chemical reaction, exponent their stoichiometric coefficient. Here, there is an important note to pay attention to, that the concentration of solids, liquid, and aqueous species doesn't figure in the expression of Kc in case of heterogeneous equilibrium. The concentrations of these species are found to have a value equal to 1. Kc also depends only on temperature, so its value changes only with temperature. As long as temperature is constant, the value of Kc is constant. And consider that Kc is unitless. Now, Kc of the backward reaction is the inverse of Kc of the forward reaction. What does that mean? Simply, let's reconsider this equation. As we saw, Kc is equal this relation. Now, if we reverse this reaction, if we wrote it in this way, K prime C would be the following, because A and B are now the product and those are the reactants. So compare Kc and K prime C. What do you notice? That simply K prime C is the inverse of Kc. It is 1 over Kc. Let's do the first application. You have to write the equilibrium expression Kc for the following reactions. They are 5. I will ask you to do a pause, to write it on a paper, and then to check out your answer. Look at the solution now. As you can see, here I have a gas and a gas, so the equilibrium is homogeneous. So I will consider in the relation of Kc all reactants and the product. This is the product, the concentration of O2, exponent 3, which is the stoichiometric coefficient of O2, divided by O3, that is the reactant, exponent 2, which is the stoichiometric coefficient. Here also, there is an equilibrium that is homogeneous, gaseous, so all of them will be considered here, respecting definitely their stoichiometric coefficient. Here also it's homogeneous because all species are in the same phase, which is aqueous, and pay attention to the 3 here, which is actually this is 3, sorry, must be 2. Now look here, this is a heterogeneous equilibrium. We have something solid with gas, with liquid and gas. What did we say in the note? That when we have a heterogeneous equilibrium, we don't consider the concentration of solid and liquid. We will consider them as constant and equal to 1. So in the relation of Kc, only the concentration of the gaseous species figures, as you can see here. The same for the fifth example, where we have solids and gases in the same phases, in the same place, in different phases. So in the relation of Kc, only the one of the gaseous species figure in Kc. Now here I will ask you to do a pause and to do it alone and then to check your answer. The solution is the following. Now let's summarize what we have seen so far. We said that the equilibrium is homogeneous when all constituents of the reactional system are in the same phase. An equilibrium is heterogeneous when the constituents of the reactional system in 2 different phases, or in many, not necessary to be 2, but it's okay. The equilibrium constant Kc, and it's denoted by Kc. This is the relation of Kc as we explained previously, and this is about the note that the concentration of solids, liquid, and aqueous species in heterogeneous equilibrium doesn't figure in the expression of Kc. They are considered to be equal to 1, and Kc depends only on temperature, and it is unitless. Now I will ask you to do a pause another time to see what you have to do as homework in the agenda, and thank you for your attention. I will see you in the